Welcome back, students. I'm your instructor for Advanced Aircraft Systems, Tom Mahoney. Today, we're going to get into lecture number 11, where we will be covering the fuel system on the CRJ 700. The fuel system is comprised of two wing tanks, one center tank, and two collector tanks. So let's take a look at what we're actually looking at so we can get started off on the right foot. Here's your wing tanks out here. It's depicted in this schematic over here. That's your left tank. This is your right tank. These are what we consider to be the main tanks on the aircraft. Uh, and then we have a center tank, which is located in the fuselage of the aircraft. And inside the main or the center fuel tank, we have two collector tanks, the left tank and the right tank. Fuel is supplied to each of the main engines and to the APU from those tanks. Of course, that makes sense. Of course, the jet engines use fuel from the aircraft tanks, and the APU also uses the exact same type of fuel. That fuel is what we call Jet A fuel. So it's Jet A fuel is nothing more than a high grade of kerosene. It's nothing highly volatile like gasoline is. So works out real well in commercial airlines. Not that explosive by any means at all. Um, very remote chance an aircraft is going to explode because there was a fuel explosion, like there was once that I know of for sure, when the TWA Flight 800 uh, exploded after takeoff from New York City. Uh, this happened back in 1997. That's when I was interviewing for TWA. Uh, the the hiring process got put on hold for about a year after that point, and then after that point, I did get hired by TWA in 1998. So that was a case where the fuel tank, the center fuel tank, actually did erupt because there was only fumes in that tank, and the pumps in the center fuel tank apparently overheated and ignited those fumes that were in that tank. At least that's the official NTSB report. Uh, some of the old TWA guys aren't real sure that was true. They think it was the aircraft was still shot down by a missile. That's a conspiracy theory, but we'll let them live with it if that's what they want to think. I happen to think it did explode because the NTSB did report it that way, and we'll just go with their story for now. So that's the theory on this so far. Let's move on to the next slide. Well, this will be the system overview. This PowerPoint is, of course, a system overview. Keep in mind that when you need to have more detailed information, and you will, because I don't go into the extreme details of any system in this class because I don't think it's appropriate at this time, but I do want you to go through your AeroSim modules for the related systems. And in this case, review your fuel system in the AeroSim modules and make sure you sync that module so I can give you credit for having completed it, and you'll get your credit for that added to your grade. The module will be covering fuel venting, pressure relief valves, two cross flow systems. One is powered, one is gravity fed. We'll talk about pressure fueling, gravity fueling, defueling, and of course, like any system on the CRJ 700, there's almost always likely to be a computer involved, the fuel quantity gauging computer, the FQGC, and we'll talk about what that does. First, let's get into where the controls are in the cockpit for all these systems and what systems affect the fuel flow. First, let's talk about the most important panel related to the fuel system, and that is the fuel panel itself. that's what the fuel panel looks like. And in the on the flight deck, it is located right up here on the overhead panel between the pilots. Uh, Generally speaking, it's kind of accepted that the captain's the one that touches the fuel switches, the first officer doesn't. But you know, the more experienced first officers are not going to shy away from manipulating the switches on this panel when the captain's not around, or if the captain's just not paying attention. Sometimes they'll have to reach up and push a switch as becomes necessary. So, of course, on the fuel panel, you have a left boost pump right here and a right boost pump right here. And then you have your gravity cross flow valve switch here, and the automatic cross feed valve here, and a couple other pumps that help move fuel side to side. Now, this panel, all of these switches are usually dark. In other words, they're not lit when they are in operation. They would be lit up when you have selected something other than the normal operation. So this whole switch will look black until you push on it, and then it would turn white, and you'd be able to see that you are in manual mode for cross fueling. So that's how that works. All of these switches are likewise the same thing. You have to push them in to get them lit up. Otherwise, they're generally dark. The APU fire push switch light, that would be this guy right here. So what we know now is hopefully the APU will shut down automatically when there's a fire detected. And if it does not, or even if it did, I'm going to go up here, I'm going to flip this plastic guard up, and I'm going to push that switch and make sure it is actually activated to be able to shut the fuel off going to the APU and hopefully extinguish a fire if we actually got an APU fire. Then, of course, if the fire continued, we come down here and push this green switch that was lit up by this time. That would be the halon fire extinguishing bottle that would dump halon into the APU compartment, help drown out or take away any oxygen that was helping that fire to continue to burn. So if I get an APU fire on the ground, I'm probably going to push both of these switches. In the air, I would probably just push the top switch and hope that the fire went out. And then we have the left hand and the right hand fire push switch lights. Again, that's this one for the left hand side, and then we have the fire push switch light over here for the right engine. All of this stuff lives right up on this panel and this panel. So that's where you'll find those switches. And then the refuel defuel control panel is a panel that looks like this. And this is not located in the cockpit. This is actually located out on the right-hand leading edge of the wing, right next to the fuselage. And this is the fueling panel that the ground crew, or actually the fueler, would be looking at, and he would be flipping those switches, opening valves so that he could pressure fuel the aircraft from his truck or a ground source of fuel being stored underground, maybe underneath the ramp area that he's pumping fuel out of up into the airplane. So we don't know about this. We're pilots. This is a top secret material. We'll get to talk about that in just another few slides. So, and I really am not going to even tell you how this thing works. Like I say, it's top secret, but you'll know where it's at. So that's that. And let's go ahead and move on with the next slide. Fuel synoptic page. So as you know by now, that you can view a lot of the systems on the aircraft with by pushing the buttons on the fuel synoptic panel, and then you can bring a particular synoptic page up in view on your screen, ICAS number 2. And in this case, this is what the fuel synoptic page looks like. A lot of information on this thing, just about everything you need to know what's going on with the fuel panel at any given time. Shows you, oh, things like fuel filters, the temperature of the fuel in the line, the amount of fuel, and there's your well, there's your main tank, your wing tanks, etc. And so anyway, just got a lot of information. We're going to go through that, and you'll see what I'm talking. Okay, the FQGC. This is not your daddy's fuel level reading gauges on his Buick. This is a fairly sophisticated computer that does a few things. What it helps us do is get a very accurate reading levels in the fuel tanks based on angle of attack. So if the nose of the aircraft is up while you're climbing out, the fuel is going to kind of want to move and migrate towards the back portion of the tanks. If you just had standard instruments inside the tank to do the reading of the fuel, they would read the fuel maybe higher or lower than it actually was because of the deck angle of the aircraft. And so in that case, the FQGC monitors that angle of attack and computes that and gives you a more correct fuel reading. In addition, the FQGC corrects the amount of fuel you have based on fuel density. So it's measuring its temperature, doing this stuff way above my pay grade. All I need to know is how much fuel do I have on the aircraft and how much time do I have to fly. Then it also monitors the fuel temperature in the right wing. So this guy here, pretty important. Actually, it completely replaces the flight engineer that we used to have on the older aircraft, where it took a 3-man crew. Now, of course, most modern aircraft only require a 2-man crew because of all the computer systems on board that help manage the systems instead of the pilots having to be fully engaged at all times. So capacity of the fuel tanks, that's kind of important. In this case, the CRJ 700 has 4,610 pounds of fuel in the center tank and 7,492 pounds in each of the wing tanks. Now, I'll tell you what, we just don't need to be that accurate. Aviation's gotten to the point with all this electronic stuff that we can measure everything with a micrometer. We still mark it with a chalk, and then we fly it using the axe method. So it's perfectly okay for me. If all you know is that the center tank is 4,600 pounds, that's all I need to know, or 4.6, and that would be good enough. And the wing tanks are basically 7.5 or 7,500 pounds. That's close enough for government work. If we need to measure it closer than that, we probably haven't given ourselves much latitude on fuel. I like to give myself plenty of latitude. The last thing I want to do is be running short on fuel because I tried to measure it with a micrometer and ended up mismeasuring or not having enough fuel. So remember those numbers, and that's good enough for me. Let's move on. So you'll get abnormal fuel alerts and quantities provided to you when the left versus right wing tanks are imbalanced. So let's say you get too much fuel on one side of the aircraft. Of course, then the airplane is not going to want to fly quite right. You'd like to keep those wing tanks balanced. And so here's what's going to happen. You're going to get a low fuel caution on your ICAS number 1. That's going to turn amber because it's kind of serious. They think, hey, you need to do something about this. Take a look at your QRH because it's an amber alert. If it's a magenta alert, that's also even more serious. So whenever you get an amber or magenta alert, you need to get the QRH out and start taking care of the situation. So when you get the low fuel alert like that, it's going to occur because you have less than 600 pounds in each wing tank. So in this case, in the synoptics page, it's showing that we have 500 pounds in each tank. That's less than 600 pounds in each tank. So that's why we're going to get this low fuel alert. We also get that low fuel alert when there is less than 1,200 pounds total. So again, in this case, we have 1,000 pounds total. But if we actually looked up here, it says 990 pounds total. So that is less than 1,200 pounds. So we again get the low fuel alert. So we could have had, oh, geez, 700 pounds over here. That would be above 600 pounds. We could have 300 pounds over here. That would give us a total of 1,000 pounds. We would then get the alert. So also, both collector tanks, we'll get the alert if both collector tanks, these guys right here, those were those extra tanks that I don't really quite understand why they're in the system, but they are. And if those tanks are low, then again, we get a low fuel alert. So that's it. That's how that works. And make sure you're aware of some of those alerts as we proceed through the course. Fuel used indication. So that's handy. I'd like to know how much fuel I used. A lot of times on your dispatch release, they'll give you projected fuel burn as you cross over certain points. And this number right up here is going to give you that information. So you'll be able to look at that, compare it to your release, your flight plan to see how much fuel you should have burned up to a certain point. And hopefully, if you haven't diverted from your flight plan and your dispatch release, those numbers should be pretty closely matched to your release as compared to what you're reading on your instruments. So it's displayed in white on the fuel synoptic page, automatically resets when you get to the gate after you've landed. You pull up to the gate, you shut the engines down, voila, the fuel totalizer resets to 0 and it starts all over. In the days when I was flying on certain airplanes, the 737, for example, you had to actually reach up and push a button next to the fuel totalizer to take it back to 0. Nowadays, it's pretty much automated, but just in case, you can manually reset the fuel used on the aircraft by going into the ICAS menu page, which would be that button right there on your ICAS or on your synoptic page. And you could go through the menu and you'd find out where you're at. You could reset the fuel in that and continue on. There are a few times when you might want to do that, just not very often. Something you can find out on the line for your line training when you make it to the airlines. Fuel temperature is important. We do not want to see our fuel temperature, at least on the CRJ, go below minus 40 degrees. Now, that's not to say the engines are going to quit, but we prefer to keep that fuel temperature above minus 40 degrees. That keeps the everything in the green for us. When it goes down below 40 degrees, we would look on our synoptics page and we would see that the temperature in our right tank where the not the indication, but the sensor is located. The sensor is in the right tank, which show us what the actual temperature is on our fuel synoptics page. And in this case, it's showing that we have, oh, hey, we've got minus 42 degrees. Tell you what, I'm just going to get rid of this guy. And just to illustrate, you would end up getting the bulk fuel temperature alert on your ICAS. And of course, it's amber. You get your QRH out again and take care of the situation. But why would that happen? Well, think about it. The temperature up, say, 38,000 feet is minus, say 48 degrees. And that's a pretty typical temperature up there. So if you're up at altitude for long periods of time, the wing tanks can actually get cooled down, and the fuel, of course, would get also cooled down. And then you'd want to have that alert to say, hey, you know what, your fuel's getting pretty cold. Shouldn't really affect us too much, except it may crystallize some the water that's in the fuel might tend to crystallize and start going through the system. Not something you really want to have. If I got a little bit of water in the fuel system, I'm not too concerned about it. I would prefer that water stay in a liquid form as it goes through the jet engine. But at any rate, uh, we would like to stay above 40 degrees with this particular airplane whenever possible. Okay, we have a device on almost every jet that I've been on. We've had this device called the fuel oil heater, and what that is it's a heat exchanger where we run engine oil through, and then fuel passes through the heat exchanger, and the fuel gets warmed up by the engine oil, and the engine oil gets cooled down by the fuel. So we've got two things going on at the same time. It's all good. Oil stays cooler and uh, fuel stays warmer. In the event that the fuel goes below 5 degrees in the fuel line, it would show up right down here. And of course, again, we would get an amber alert up on our ICAS that says, in this case, left fuel low temperature. And it would be an indication to us that something has failed with our oil fuel oil heater, and for some reason the fuel is dropped to a temperature lower than 5 degrees. So that's just an alert we'll get. We would want to try to take care of that if we have the opportunity by reading the QRH. The fuel filter, that's another item in the fuel line system. Let's take a look. The fuel filter in the schematic is located right down here on both sides for each engine. And if we end up getting a fuel filter clogged up, it will start to show low fuel pressure going to the engines. And then, of course, we would get this alert right here. Now, that's, of course, something we don't want to have happen. We don't want to have a dirty fuel filter, because then we're not getting the fuel cleaned out effectively enough, and the pressure is going to drop. But one thing that I can say about this, almost in all cases, the fuel will end up bypassing the fuel filter if the fuel filter gets clogged up. So if it gets clogged up and fuel can no longer travel through that uh, plumbing, it'll come around to the outside and come back up this way. Uh, the moral of the story is it's better to get dirty fuel to the engine and keep the engine running. But if we'd really prefer to have clean fuel going through the filter. But hopefully we can take care of some of this stuff by going through the QRH. It would probably tell us what to do. There may not be anything we can do to fix it, but it might tell us what action we need to take, like hurry up and let's get this thing to the destination airport so we can get on the ground and get that fuel filter cleaned out and properly operating. Automatic fuel transfer. Now, this is a great system on this airplane. I really like it because I've been involved in it. Oh, let's see, two incidences. One where I caused it myself, where I got the jet fuel out of balance between tanks, and then I had a little chuckle. I was with a captain friend of mine as a first officer. He decided to cross feed the fuel during the descent, and I looked at him. I said, "Well, you know what? We don't have the engines up to power on the descent. Fuel's not going to really cross feed very fast, or balance. We won't be able to get the tanks balanced that well." But he said, "No, I'm going to go ahead and do it anyway." So he flipped it. Of course, we were going into Denver, then started getting vectors clear around the airport off-route vectors. The next thing we know, we forgot to switch the fuel pumps back on the non-operating wing side, and the next thing we know, we get an alert we're out of balance just before we land. So we had to hurry up and try to get the aircraft back in balance. We just got it back in balance. I was kind of snickering, and the captain's looking at me like, "Yeah, okay, I understand. That's why we don't turn. That's why we don't balance tanks here during the descent." So he got the message. I got a snicker out of it. I didn't feel like being so stupid early in my career when I did basically the same thing. So at any rate, this is an automatic fuel transfer system, works real good. So let's talk about it here. So what we have is we have our wing tanks we mentioned earlier, and we have our main tanks right here, and we've got our collector tanks and so forth. So let's see how this fuel moves from one tank to another. We have what we call a transfer ejector, and I think of it as a transfer ejector pump. It's not really a pump, but it acts in the same manner when you've got basically a vacuum that can get these things started, then they'll continue to eject fuel from one tank to another tank. So the transfer ejector is this guy right here, and it's labeled as such right there. You see transfer ejector, and you have that on each side of the main tank. And the transfer ejector is connected to a ducting that brings the fuel over into the wing tanks. Okay, and of course you have to have the valve here open. You see that valve right there. That valve would have to be open for this to occur. So when you are operating in automatic mode, fuel will be taken out of the center tank when there is fuel in the center tank. It will be transferred out to the wing tanks. And the way that does it is when the wing tanks use up fuel and get below 94% full, then the transfer ejector starts pushing fuel over into that tank. So when this tank gets to be 94%, you start transferring fuel automatically from the center tank to the wing tank. So let me back up just a little bit here, explain how this all works. In the big picture, fuel goes from the center tank to the wing tanks. From each of the wing tanks, it goes to the collector tanks. From the collector tanks, it is ducted or plumbed over to the engines, whether it's the engines or the APU, doesn't matter. They all get, the engines and APU get their fuel from the collector tanks. So it's first the fuel goes out of the center tank, wing tanks, then collector tank, and then to the appropriate engine. That's the big picture of how it works. And as I said, the fuel will be pumped over from the center tank into the wing tank when the wing tanks get down to 94%. It stops pumping fuel into the wing tank when the tank is filled back up to 97%. Okay. So the other thing that's important to understand, and we'll talk a little bit more about this when we're talking on the fueling slides, but we always burn fuel out of the center tank first, and then we burn fuel out of the wing tanks. And we always fill the wing tanks first before we fill the center tanks. This has to do with the zero fuel weight, and we'll again talk about that. I just wanted to give you that a little upfront information as to why it's doing what it's doing. Then we have the scavenger ejectors, and the scavenger ejector is right here. It sets in the wing tank, and it brings fuel across from the wing tanks into the collector tank. Those are what we call the scavenger ejector. They're just like the ejectors up here. They just have different names for their locations. Then we have the main ejectors, and they are located right here. Of course, you have the mirror image on the opposite side of the aircraft. That says main ejector there. And the main ejector is the source that provides fuel to the engines when the engines are running. If the engines are not running, the ejector can't supply fuel because there is no suction. And so therefore, the ejector pumps have to have some sort of suction or siphoning process to get the fuel out of the tank that they're located in. If they don't have the engines running, there's no siphoning. And in that case, to get the engine, if the engines aren't running, you're trying to start the engines, then you have to first turn on the electric boost pumps right here for each engine. And then you'll be able to supply fuel through the ejector, main ejectors to the engines once the engines are running. Won't work that way. The ejectors don't work until the engines are running. So that's why we use the boost pumps to get them going. Caveat on this is you only need one fuel pump turned on to actually make the ejectors work in either tank. So it doesn't really matter which pump you have, just get one on and it's going to work. But normally, as a matter of practice, we turn both pumps on. So there you have it. Those are your ejectors. And there's the transfer ejector, the scavenger, and the main ejectors. Fuel boost pumps. Well, we mentioned those in the previous slide. We'll do it again. Prior to the start of the system, you have to, the system is unpressurized because the engines aren't running. So you have to pressurize the fuel system using the electric pumps. And in this case, if we were trying to start the engines, we'd have to turn the boost pump on. It shows that we have fuel at least going as far as the engine shutoff valve. Also in the left collector tank right here, this side, we have another little fuel pump right here, and that's what provides fuel to the APU that would be setting down in this area. So the APU fuel pump has to be turned on in order to get fuel to the APU. And when you turn that pump on, you actually automatically open the APU shutoff valve at the same time. So two pumps in the left side, one is the APU pump, one is the boost pump for the left engine. And over on the right collector tank, you just have a boost pump for the right engine. Okay. Those boost pumps, the engine boost pumps, are controlled by this switch located right below that symbology right there, the lettering right there. So this is our pump. And when we push the switch in, it will go from dark to, we get white and on, enunciated on the switch. So now we know that the boost pumps are operating to get the engine started when we need to start it. These jet engines simply will not start without the boost pumps running. And again, once the boost pump is running, then, or once the jet engine is running, then you can turn the boost pump off and the engine will continue to be fed by the main ejectors from the collector tank. All clear? Good. Let's keep moving. Engine fire shutoff valve. Okay. So remember we talked about that switch up on the eyebrow panel, you know, which side of the aircraft you're on. There's a switch for the left engine, it's a switch for the right engine. In this case, we're talking about the engine fire switch, and this schematic happens to show where we've probably got a fire. Well, let's see what it says here. In the event of an engine fire, the engine fuel valve can be selected to the closed position by pressing the engine fire push light switch. So it's definitely going to close this valve here. And if that happens, we're going to shut fuel off to that engine. Along with, at the same time, we're going to be turning the hydraulics off, disconnecting the generator relay, silencing the bell, and various other things that we remember by the acronym FATFIS. We'll get into that later on when we start talking about fire protection defects. But that's an acronym I learned when I first got into the airline business. So FATFIS, keep that in mind. We'll talk about it later. Um, so the fuel valve will be driven to the closed position, preventing additional fuel from entering the engine nacelle. That's a good thing. If the engine's on fire, you certainly don't want to keep feeding the fire, especially with fuel. If the valve fails to close, a left or right engine shut off valve fail alert illuminates. And I don't know if I have that up here. Nope, I guess I don't. But this would illuminate on your ICAS panel, number one, and it would be time to do something about it. Get the QRH back out and make sure you follow the instructions. So that's where that fuel shutoff valve lives. One is over here. And as I said, if you have a fire, that's the valve you'll end up closing. APU fuel. Well, we've already mentioned it a little bit, but APU fuel is supplied from the left collector tank right here. And of course, our APU lives right down here. And the APU fuel is supplied from the left collector tank. Selecting the fuel, the power fuel switch on the APU panel turns on the associated, well, not boot pump, but actually boost pump. I'll fix that here. There we go. It's fixed. Boost pump. So the boost pump comes on and it opens the APU fuel shutoff valve at the same time. So you look up the APU panel, you push the power fuel switch. This pump is going to turn on. It's going to open this valve, and on your status page, you're going to see it show up here as APU SOV open, which is this guy right here. So here, that enunciation relates to that. You'll notice it's not in amber, it's in white. It's just an informative ICAS for you to let you know that, hey, this is what the system is set up to do. If you wanted to, you could go to the fuel synoptics page. You could look down here where that same valve is located as it is up here. And in that case, you'd know that the valve was also open by looking at the fuel synoptics page. So either way, a lot of different ways to see how the aircraft systems are working. Personally, I like to look at the fuel synoptics page just to verify, to give me a visual look. And then I go, oh yeah, it is open. Then I come back to my status page. And I say, oh yeah, well, there it is. I really went through a little extra work to have to verify something, but it's good. Doesn't matter. Okay, if we get an APU fire, we're going to get an alert, and it's going to say, although an APU should automatically shut down when the APU fire is detected, the APU fire push light switch should be pushed to manually close the main APU SOV shutoff valve. This is an action that will prevent additional fuel from going into the APU compartment. So just like the jet engines, we want to shut fuel or a source of ignition off. So we would go ahead and push that APU fire push switch, push it, and then once that is pushed, we can be assured that this valve is going to close, then restricting the flow of fuel to the APU. If it happens to stay open, we're going to get this indication, APU SOV open, and that would not be a good thing. We could go to the synoptics page, and this is exactly what we'd see. We'd see a red line, get your QRH out, and do what it says to do. In the meantime, I'm going to be getting my finger ready to blast off that halon bottle in case the fire doesn't go out. Maybe I can get the fire out without having to turn the fuel off. But at any rate, get that QRH out and get through it as quickly as possible in this kind of situation. All right, let's talk about the fuel crossfeed system. This is what keeps the fuel balanced between tanks. So a couple different ways of doing this, depending on what you're doing. I would prefer, since this aircraft has the capability, to put this system into automatic mode. If I put it into automatic mode, the aircraft or wing tanks should stay balanced reasonably well to each other. So the fuel crossfeed operations are either automatic or they're manual, as selected from the light switch on the overhead fuel panel. So if you remember, we talked about this fuel panel here being on the overhead panel up in the center. And so we can select uh, the system to operate manual or automatic by pushing this switch, the one that's outlined right here. So if the FQGC detects a fuel imbalance greater than 800 pounds, a caution is generated on our ICAS panel. So voila, out of more than 800 pounds out, we get an alert, hey, you need to start balancing your fuel up. When in automatic operation, and automatic is when this is a dark switch, is an operation, the fuel will automatically be transferred from the center tank to the wing tank. So let's take a look at this and see what it's actually doing. As you can see, we have on the fuel synoptics page, well, it would actually be up here. You can see that we have an arrow here, and it's actually pushing fuel in automatic mode in this direction from this wing tank. So it would be pushing fuel from that wing to the other side. Okay. Now that's a good thing. And you can see that the tanks are showing out of balance. Okay. So it kind of keeps it in balance. That's a good thing. If the right wing tank got lighter than the left wing tank, you'd have this arrow pointed in the other direction. In the event a cross-feed pump failure occurs, so let's say this pump that's located right here, that goes bad on us. Tell you what, let's get rid of the line so it's more clear. Let's say this pump fails or goes bad, quits doing its job in the automatic mode, then we can do something called gravity feed. And that simply means we are going to open up this valve, and that is going to be this button right here. Pushing that will open that valve, and then if we're on straight and level flight and coordinated, in other words, not pushed on the rudder in a skid or a slip of something like that, what will happen is the wings will stay level and the fuel will migrate from the fuller tank to the less full tank until both tanks are roughly the same in fuel volume. So that's how that would work. It's just a gravity feed. Not a great way to do it, but if we ever had to and this pump failed, we'd certainly want to go ahead and do the gravity feed. We just got to make sure that the aircraft stays rudder trimmed correctly and level at least 1G straight down in relationship to the longitudinal axis of the aircraft. So that pretty much covers that. Let me just go to the next slide to make sure we've covered everything that we want to cover on here. Nope. Let's go back one thing. There's one thing that has not been discussed here. So you notice that this push switch has been pushed because we have an illumination here. It's showing us that, okay, they're going to cross feed manually. So this, we're not gravity cross flowing, we're going to manually cross feed. So what would happen is we'd push this in and this switch would be turned white and we get M, A, N, manual right here. illuminated right in that area. Then we know we were in manual mode. And at that point in time, we can manually cross feed from the center tank or take fuel out of the center tank over into the main tank. And we would do that by pushing the left uh, ejector pump and valve to the on position. And then we would be moving fuel into that side of the aircraft, to that wing, the left wing in this case. If this was off and this one was on, we'd be moving fuel in that direction from the center tank. So that's simply how it works. It's not bad. If we push both on, it's going to kind of cancel itself out. Things aren't going to work the way we want it to. So review that in your AeroSim. Get familiar with how that works, and hopefully you'll just be able to keep everything in automatic in your career and won't have to worry about all this stuff. So aircraft fueling. This is kind of something we as pilots don't get involved with very often. Sometimes we do because there might be an anomaly on the fuel gauges and we have to actually go out and check to make sure the fuelers are getting the aircraft fueled properly so we know what's actually happening. Let's talk about it. Fuel and defueling is performed by highly trained professional aircraft fueling technicians. This requires specialized handshake. We don't know. Pilots are not authorized to know the handshake. Pressure fueling is done at the right inboard leading edge of the wing. So they've got a panel that they open up, and voila, inside that panel is this fuel control switches. And we call it the fuel control panel. And this one, I wouldn't even want to begin to try to learn. Looks too complicated for an old farm boy like me. You know, I'm used to filling up tractors. I'll just stick the nozzle in there and start hand pumping the fuel in from a tank in the pickup. But in this case, a little more sophisticated. So you would have to flip these switches correctly, and I'm sure they have a shut off that automatically shut off when the fuel level in each tank gets to where it needs to be. And that's how they accomplish the fueling in some respects or another. Gravity fueling, we can do that. Let's say we get out to a little podunk airport where they don't have a fueling truck that can pump the fuel up into the wing. Then we might have to do over the wing fueling. And it's accomplished through wing caps that are like right about there on each wing. And you can open those caps up and begin fueling over the wing. Now, the caveat here is if the wing tanks were mostly full already, the fuel out in this part of the wing is going to be higher than the caps. And you pop those caps off, all this fuel is going to rush out, and you'll get fuel all over the wings, all over the ground. So something I wouldn't recommend doing is popping those caps off if you have full wing tanks. I might do it if we were in desperate need of some fuel to get put into the wing tanks, but I would want to make sure that fuel level was below the level of where the caps are. The fueling control panel can be, by the way, that's important. The fueling control panel can be operated on battery power. So this is an electric panel. If it's not powered, it won't work. So they keep it hooked to the battery direct bus in most cases. So that if the fuelers get out there on a dead airplane that's not powered up, at least their panel stays powered so that they can open and close valves on the air tanks and get the aircraft fueled before pilots get out there and actually electrically power up the aircraft. Fuel quantity is measured in pounds. We do not operate in gallons in the airline industry. Everything is pounds. We fly based on pounds, right? How much does the aircraft weigh? We want to know in pounds so that we can calculate our center of gravity, our takeoff weight, these kind of things. So fuel is measured in pounds. Now coming out of the truck, it's measured in gallons, but the fueler has to convert those gallons to a the amount of pounds that he actually put on the aircraft. So he's going to be adjusting his fuel quantity based on the fuel density, which most of the time the fuel is going to weigh somewhere in the neighborhood of about 6 pounds. But to be more precise, they'll get their little book out and they'll go through, figure out which column they need to be in, what's the temperature of the air that day, what's the fuel density, and calculate how many pounds of fuel they actually put on based on the number of gallons they actually unloaded from the truck. Main wing tanks are normally filled first, however, additional fuel followed by additional fuel going to the center tank. And of course, the center tank is emptied first, and we always keep fuel in the, we always use fuel out of the wing tanks last. Now, that's due to what we call zero fuel weight. So right in this area of the aircraft where the wing joins the aircraft, that is where most of the stress is placed on the wings. So the aircraft, the zero fuel weight becomes an important term that you're going to need to understand as you progress with your career. If we had the aircraft, say it was the gross weight was, say, limitation was 100,000 pounds, we wouldn't want to put all the weight in the fuselage and have very little weight on the wings, because then we could snap the wings off at the roots if we overloaded it in some sort of G-force. So we have to make sure that we do not load the aircraft greater than what is authorized by the zero fuel weight, meaning that we can only have so much weight in the fuselage before we have to start adding weight to the wings, and adding weight to the wings is going to be in the form of fuel. That's how we get zero fuel weight. So it's a limitation primarily because of the structural limitation of the aircraft at the wing roots. Okay, the rest of the fueling processes are top secret and are contained in documents, secret documents at Mar-a-Lago. Did you get it? Secret documents. Okay, apparently not. All right, enough of being political. We'll move on. Magnetic level indicators. This has always been kind of interesting to me. I think this is kind of a neat measuring stick. You know, normally you think you can put a dip stick in to the top of the wing, like you do on your Cessna. You have a little tube that you stick down there, hold your finger on top, you can pull it up. You can get an exact measurement of how much fuel is in that wing tank for like a Cessna. Well, we kind of do the same thing, only we do it from the bottom of the wing on a jet. Because the tanks are so long, we have to have what we call magnetic dripless sticks, or we call it sticking the tanks. And these sticks are located throughout the bottom of the wing on the aircraft. So I'm not sure exactly how many are on this aircraft, but on some of the aircraft I've been on, there's been 4 to 6 sticks that drop out of the bottom of the wing along the wing in these areas right here. So what this does is allows you to measure how much fuel is at what the level of fuel is at along the length of the wing. So you get a very accurate measurement of fuel using this manual method of measuring the fuel. Caveat is you have to make sure that the aircraft is level. So usually in the nose wheel, someplace like that, maybe in the main gear, there's actually a little pendulum bob that tells you how level the aircraft is sitting on the ground. And that has to be taken into account when you do this. Generally, the pilots don't do this. This is the fueler's job. But if they're going to be doing this, the captain is usually involved in watching what they're doing so that nobody makes a mistake and miscalculates something, because it is a little bit tricky on the calculation. But let's talk about how these things work. So this is the bottom side of the aircraft right here, and this is showing the dripless stick being flush with the bottom of the wing. And you would take a screwdriver and you'd put it right up inside here, give that a 90-degree twist, and then this stick is going to drop out from underneath the wing. And it'll drop all the way down. And you want to pull it all the way down, and it'll bottom out against up inside here against the bottom of the tank. And then you push it back up. And then this shows a pretty good illustration of what happens. So the stick is all the way up inside, and then you pull it out, you pull it down all the way down, then you push it back up. And there's this thing right here. And it's kind of like a magnetic cork that's floating on top of the fuel around a tube inside the tank that goes all the way up and down that's sealed. So when you pull this dripless stick down, no fuel comes gushing out because the tube is sealed at the top. And then you push this stick back up, and there's a magnet or a piece of metal on the end of the stick and a magnet on the float, or vice versa. And anyway, the magnet, the float and the top of the stick become attracted magnetically to each other. So the float, which is floating on the outside of this main tube, floats up and down on the fuel, and the stick then figures out where that float is, holds itself in position, and then you can read right down here at this point what the fuel level is for what that stick is measuring at for that given location in the tank. That's how it works. You have several of those. You pop the sticks down along the wing, take the readings, and figure out with a combined total of those readings what your fuel level was in your tanks, and then calculate from there how many pounds of fuel you had on board. So if your fuel gauges weren't working correct in the cockpit, this is how you would get to the initial fuel reading. That's good enough for the FAA. We know how much these engines burn, and if you fly normally, you'll end up with the correct amount of fuel that you projected when you get to your destination. Okay, guess what? We're getting a little closer. This module's complete. Don't forget, go back and look at your RSM modules, and when you're done, sync so I can see it. Until then, have a great day. Love my job. Glad to be here. Hope I can make a difference.